Thank you for this opportunity to present our work as part of this year's Nature for Life Hub. My name is Gaël McGill, and today I'll be presenting on behalf of my collaborators Dr. Eric Shivian and Jeannie Park. We have been developing a new argument to promote the preservation of biodiversity. We can all agree that humanity faces significant engineering challenges in order to live sustainably on this planet. Some of these challenges include the storage and production of energy, heating, cooling, and ventilating our buildings, moving through air and water more effectively, and how to make the strongest, lightest, most biodegradable materials possible. But very few appreciate that the answers to these challenges have already been solved by the plants, animals, and microbes all around us. Consider that natural designs are so incredibly efficient because they have been refined over millions of years of evolutionary time. Only the successes remain. By this process of natural selection and elimination, nature has in effect done our engineering field trials for us, and we would be wise to listen. Take, for example, dragonflies. They are nature's oldest flyers and have been around for about 300 million years. Their acrobatics are unmatched by any other flying organism. How do they achieve such aerial agility? Let's focus on wing structure. Most of the time we are looking at dragonfly wings from the top. But if you look at cross-sections of that same wing, you notice that it's a corrugated surface with ridges and grooves. Scientists like Professor Akira Obata have realized that this corrugation, unlike an airplane wing, creates micro-vortices that spin within the grooves of the dragonfly wing. The vortices behave like miniature ball bearings that effectively create a fluid-on-fluid system that lubricates the wing surface and eases the flow of air, reducing drag. This has led Obata and others to design micro-wind turbines that have better performance at a wider range of wind speeds. They're more efficient at harnessing wind power, partly because they start spinning at lower wind speeds. Let's now turn to gliding and soaring birds. Birds have been models for flight for hundreds of years, but there are two features of gliding and soaring birds in particular that are having an impact on today's aviation industry: wingtips and slotted wingtips. When air flows over an airplane wing, there's a difference in air pressure between the bottom and the top of the wing. As the wing tilts upwards, known as the angle of attack, and generates lift, the air pressure under the wing is higher than that over the wing, and this difference creates a vortex at the tip of the wings. This swirling tunnel of air expands, results in increased drag, and translates to decreased fuel efficiency. You may have noticed that almost all commercial planes are now equipped with winglets, a bio-inspired design pioneered by Richard Whitcomb. It's estimated that these winglets have saved more than 10 billion gallons of fuel. That's like taking 20 million US cars off the road for a year, and reduced CO2 emissions by 105 million tons, which is like planting about 40 million acres of trees. Gliding birds have also slotted wingtips. Their wingtip feathers can come apart. You can see this in the turkey vulture picture on the left. And this also results in a series of smaller vortices that further reduce turbulence and drag. This feature is also being explored in the design of new airplanes. Water, like air, is also a fluid, and swimming organisms have much to teach us about how we can more effectively move through fluids. Take humpback whales, for example. These slow giants of the sea may in fact be one of the greatest acrobats of any marine animal for their size and weight. One behavior in particular showcases their abilities: bubble net feeding. The whales hunt in packs and encircle schools of fish by emitting a cylinder of bubbles that acts like a net. The fish are driven upwards towards the surface, and the feast begins. Up to half a ton of herring a day can be consumed by a whale using this method. During this behavior, the whales are making very tight turns in the water, banking at sharp angles and high speeds. Remember, these are 50-foot, 30-ton animals. How do they pull that off? Well, the secret to maintaining speed at such extreme angles is likely in the shape of their flippers. Along the leading edges of the pectoral flippers, like the one in this picture, you'll notice rounded swellings called tubercles. They have a scalloped appearance. What is it about these structures that allow whales to achieve high angles of attack in the water without stalling? Professor Frank Fish and others have studied the dynamics of flow over whale flippers and found that the flipper tubercles are creating small spinning vortices that are perpendicular to the axis of flow, which accelerate fluid flow over the flipper and pushes any turbulence backwards away from it. And this design has now been applied to several human-engineered products by the Whale Corporation, from turbine blades on the left to cooling microfans in computers on the right. Finally, I would like to address the argument that surely it is not necessary to save all organisms, since the natural designs we're referring to must exist many times over across families of species. For example, there are roughly 3,000 species of dragonflies alive today. How are these different, and do we really need all of them? Take, for example, the globe skimmer dragonfly on the left. It's capable of the longest non-stop flight of any insect, over 4,400 miles. Its rear wing seems to have a different aerodynamic design. But what do we really understand about the difference between these two species? Very little. If we lose one of them, we may never know which is the optimal design for our purposes. These examples and many more are available as part of a booklet we have recently published and that is being distributed with the help of the United Nations. In closing, and as part of our other booklet on human health and biodiversity, I have to mention the role of human activity and biodiversity loss on the spread of infectious disease and specifically zoonotic diseases. These are diseases like HIV/AIDS and likely COVID-19 that have spilled over from wildlife to humans. Zoonotic viral transmission is driven not only by the vast wildlife trade for food and exotic pets, but also by deforestation, climate change, and more intense agriculture. As a result, we push animals out of their normal habitats into greater contact with people. It's estimated that 10,000 viral species capable of infecting humans currently circulate silently in wildlife. So let us learn the lessons from the tragedy of the recent pandemic and share an awareness of the importance of biodiversity, not only for our health, but also for our ability to find solutions to the engineering challenges that will enable a more sustainable future. As the former Director General of the World Health Organization said, "The library of life is burning, and we do not even know the titles of the books, much less what is in them." If we continue to cause the extinction of species at the current rate, we risk losing the treasure trove of natural designs that nature's biodiversity provides us in order to meet today's engineering challenges. Therefore, we have no choice but to protect biodiversity, and in doing so, to protect ourselves. It is not just the right thing to do, it is a matter of survival. I want to thank everyone who was involved in helping us develop this material and encourage you to download our booklets from our website, naturestoolkit.com. Thank you.